It's very important to learn. All right. So today I forgot the roll sheet again. I still don't have an office. I still don't have a printer. So maybe next time. Okay. So housekeeping stuff. Warm up 1 is due this Thursday, and if you turn it in tonight, by the end of tonight, you get 10% extra credit. If you turn it in by the end of tomorrow night, you get 5% extra credit. Okay. All right. By the way, the class has started. It's a small room. If you talk, it's going to interfere with the class. And if you really need to talk to somebody, you can, feel free to step outside, talk, and then come back in here. Okay? And that's perfectly fine with me. Okay? I just don't want you to disturb other students. And this class, we're going to go pretty fast. Anyways, if you need to talk, go outside. All right. And again, as I mentioned before, I'm going to remind you every time, if you have code from previous semester, be very careful not to copy from it. Best you get rid of it, especially towards the end of getting close to the deadline. People get desperate and say, my code doesn't work, what do I do? And then you copy some code. Okay, so please, don't do that. And again, the reminder is that the grading guideline is the only way we can grade, so make sure you run through it. Make sure you have done the GDB exercise we mentioned. Okay, draw a picture. It's very important to learn how to draw a picture, write down memory addresses, and write down the content of memory addresses. Sooner or later, you're gonna end up doing that a lot. Okay, so might as well. This is the good time to do it. You need to learn Unix, install Ubuntu 12.04, and start looking for a kernel partner. One thing that I got a midterm and the final exam room for this class. It's kind of crowded over here. So it's going to be in SGM 101. SGM is the building, I guess, right north of the OHE building. And I guess you can click on the map to find the location of it. All right. So let's go back and talk about processes. And again, we're in a rush. Trying to finish threads, chapter 2 of the textbook, to get you ready for warm-up assignment number 2. And I posted in the class Google group. Again, please read every one of my posts in the class Google group. I mentioned that, we're a little behind in lectures because, when I was planning for the class, I didn't realize that last Monday was a holiday, so we're 1 lecture behind. So what I'm going to do is that this Thursday, I will have a sort of a pre-taped lecture. So I'm going to go into a room all by myself, record a lecture. And that will be the lecture right after this Wednesday's lecture. Okay, so in a way, this week we'll have 3 lectures. One of them you don't have to attend, and that should be able to cover the entire chapter 2. Okay. All right, and if you want to go ahead with warm-up number 2, you can read the slides on warm-up number 2. And also read chapter 2 textbook, and also scan ahead on some of the lecture slides. Okay, that's one way to get started early. All right, so today we're gonna try to finish up with the processes and talk a little bit about files. Some of this file stuff I already discussed it in the class Google group, telling you about standard input and standard output. So we're gonna talk a little bit about that. A little bit recap from last time. Okay, so last time we talked about system calls. So the idea, and also traps, right? So the idea is kind of like this. I'm going to draw this kind of silly picture that your user program is running over here and it's going here and there, running around. And there are these trapdoors that you're not you might not be aware of. So there are these trapdoors. If you step on them, you fall below the user space. Okay, some of these trapdoors are there on purpose, and you can actually you can actually sit yourself right on top of it. You press a button, and voila, you're down in the operating system. Right? So these are called system calls. Okay? There are also traps that you're not aware of. If you come over here and you execute an illegal instruction, you also get trapped into the kernel. Okay? If you do a divide by 0, if you access memory location 0, you also trap into the operating system. And over here is the big operating system. They catch you and they try to figure out how did you get into the operating system. Okay? You say, oh, you do a divide by 0, and, and then your process dies. Okay? If it sees you try to access memory location 0 again, it lets your process die. But if it turns out to be one of these controlled access point, right? These controlled access point. And on Unix, there are probably less than 256 of them. Okay, so if you just happen to be dropping into the kernel because you're going through this control access point, then the kernel will say, oh, I'm performing a service for you. I'm going to do something for you. And eventually, when I'm done, I'm going to return you back into the user space. All right, so that's basically what traps are. Okay, so last time we talked about dealing with processes, right? We talked about fork, we talked about exec. We talk about exit, and we talk about wait. Okay, and we were creating a picture, and this code basically put all the 4 system calls together. Okay, so here's a parent process, calling parent process right here. It forks off a child process, right? It calls fork, and now both the child and the parent, they're executing the same code from this point on. Okay, the only difference is that when the child starting to continue to execute, the process ID will return by fork is going to be equal to 0, and the parent process, the return, ID is going to be the ID of the child process. Okay, so you can do an if statements over here to say if the fork return ID is equal to 0, okay, then you do this statement. So which means that the child process, the next instruction it will execute is this statement. Okay, if the parent execute this statement, well, fork is going to return a non-zero value. So therefore, the non-zero value will get stored into PID, and the parent is going to come here and execute the wait statement. Okay, so it's a little confusing because now we have 2 things executing in parallel, and even though we only have one single processor, okay, we sort of want to create the illusion that these 2 things are in parallel. Okay, so how do you create that illusion that these 2 things are in parallel? Well, one thing that you can say is that the abstraction we're going to create is that you really have no idea who's going to run next. Okay, so it is possible that the child will run next. It is possible the parent will run next. Anything can happen, right at this point. Okay, so therefore, they create the illusion that these 2 things are sort of running in parallel. Okay, so when you write your program, you shouldn't really control, who's going to run next. Maybe you will, do some measurement and say, oh, on this operating system, this guy always run next. Okay, don't do that. Okay, make sure when you write your program, you're going to assume that all these things are running in parallel. And you're going to write your program in a certain way so that, when everything's running truly in parallel, it will still be okay. Okay, if you have a multiprocessor, then it is going to be the case where the child process can execute right here in one processor, and the parent process will execute right here in another processor, and this can be done in parallel. All right? Okay, and over here in this example, the child process, okay, is going to call exec_l, wiping out its address space, right? The last slide of the last lecture. I guess we sort of saw that already. Oops, I guess that doesn't work. Okay, when you call exec_l, the address space of the child is going to get replaced by whatever program that was specified there, right? So in this example, the one that gets specified over here is the primes program. So it's going to compute primes, okay, and it's going to take one of the command line arguments, say I want to compute the first 300 primes, and then put them in an array, and then do nothing about it. Okay, so the child will run in that example. Over here, there is a line here that says exit 1. Okay, so if the child actually, if you do a fork successfully and the child execute the exec_l, then this code is gone from the child process, right? Because the child process replaces its entire address space with a program called primes. Okay, so therefore this code belongs to the parent process, right? So this entire code is wiped out. Okay, so why is there exit 1 right here? Okay, as it turns out, it's there just in case exit_l failed here. Okay, how can exit_l fail? Well, for example, you compile this on your machine and you run on a different machine, and it turns out that there's no path called /home/bc/bin/primes, then exec_l will fail, and then you come to the next instruction, and then you call exit. Okay, so the exit over here, it's not to exit the child process. Well, it's not to exit the primes process, but to exit the parent process in case exec-L fails. All right, and you should always, you know, be a little paranoid. Don't be 100% sure that every API is always going to be successful. Okay, so therefore you have to put to exit 1, you know, right here. Okay, if you don't put exit 1 over here, what's going to happen? Okay, the child is going to call it exec-L failed because this program doesn't exist. Then the child will actually execute the next statement, which is going to be the while statement, if you don't have the exit. Okay, then it will become very interesting. All right? Okay, so we're going to see what this all look like, put it all together, so to visualize what's going on. Okay, so again, over here, we're going to draw this line right here to say that above this line is the user space, below this line is the operating system. Okay, of course, you can also draw another line over here. The hardware is over here, so you have CPU, you have memory, you know, etc. Okay, so keep that in mind. All these things are there simultaneously. All right, and the operating system there is to provide a service. Okay, so we're gonna simulate this code. Okay, this is the code that we saw on the previous page. Okay, now you only have the parent process running right over here. Parent. In this case, we'll sort of assume that the parent is the login shell, and the login shell is going to fork off the primes process because the user type primes 300. Okay, so the login shell, what it will do is that it will say primes. Where's primes? It's going to try to look for the location for this prime program, okay, and then pass it as the first argument, right? Just like in this case, whoops, okay. It will pass as the first argument. It finds the location of this program, okay, run it this way, okay, and now the child process is going to start running, right? Okay, so we're going to see exactly what will happen over here. So in this case, the parent process is going to call fork. Okay, fork is a system call. So you trap into the operating system. All right, so the picture I'm going to draw over here is that the operating system is going to have multiple components: process subsystem, file subsystem, you know, virtual memory subsystem, networking subsystem, a bunch of subsystem, you know, put in ... over here. So in this case, it will trap into the operating system. Okay, at this point, the parent process is suspended, right? So we're going to sort of imagine that over here, we only have a single processor. The processor can only do one thing at a time. Okay, so if you're executing in the operating system, well, you're not executing the user process. Okay, so therefore, the parent process is suspended. How do you suspend a process? Okay, you have to save the context of the process, or in this case, there's a thread running in the process. You need to save the context of the process or the thread into a context, you know, memory location. Okay, so this picture I show over here is that inside the kernel, this is the process control block, PCB, of the parent process. Okay? Inside over here, you can store the context of the parent process. Okay? So as this process makes a system call, it goes into the kernel, the current context of this process gets stored into this context area. Okay? To be more precise, over here we have the CPU. Okay? When the parent process was running, it's running inside the CPU. Okay, right when you execute the trap instruction, what happens is that all the state inside the CPU get written into the context area. Okay, so this is how you save the context, and the reason you want to save the context is that later on you want to restore the context. Right? You're saving the context because you call fork. Okay, when you restore the context to have this parent process run inside the CPU again, what happens is that that one is going to continue execute from this instruction. All right, so this is just part of the context that belongs to the CPU. Later on today, we're going to see some other context are stored in some other parts in the operating system. Okay, so this CPU-related context are stored over here. There might be other contexts that are stored inside the, you know, the file subsystem or other subsystems. Okay, the context is actually spread out for one process all over the kernel. All right. So now you trap into the operating system. Operating system, you know, caught you and say, oh, you are making the fork system call. It's one of the 256 system calls. So it will actually, you know, provide a service for you. Okay. So in this case, this service is to create a child process. Okay. You create a child process to be identical to the parent process. Okay. So therefore, this one. I draw over here the child process. The child process is still the login shell. because it has exactly the same contact in the address space, has the same code segment, has the same data segment, has the same stack, has the same heap, has the same everything. Okay, so now the child, who is executing right now? Well, the operating system is still executing, right? So therefore, the child and the parent, none of them are executing. So over here, I also draw the context for the child to be stored inside the PCB of the child process. Okay, so the child hasn't even running, but since it's the exact copy of the parent, well, these two contexts should be the same, right? Okay, so later on when I run the child again, basically what I'm going to do is I'm going to take this context, and then over here I have the CPU right here. I'm going to put the context into the CPU, and as soon as you do that, the child process is running. Okay, so therefore, where is the child process going to continue executing? Exactly the same place as the parent. The child is going to execute from here if I return to the child. If I return to the parent by writing this context into the CPU, then the parent is running, and it's going to be running at exactly the same place. Okay, so it's kind of weird. Okay, but both of them will run at exactly the same place. The only difference is the return code for the fork, system call. One of them will return 0, and the other one will return the process ID of the child. All right? And then remember, this is PCB, right? Inside PCB, there is the process ID, there's return code, there is the, the linked list for the dead children, and then there's the link and all that kind of stuff, as we mentioned in the last lecture. All right, so everything sort of need to put together. All right, so now the operating system created a child, okay? And what it will do is that it will return, while we have no control, maybe it will return to the parent, it will return to the child, it will return to one of them. Okay, in this example, we're going to pretend that it's going to return to the parent first. Okay, it's doing this first because we want to have a single processor, so you can only do one thing at a time. Okay, if it returns to the parent, what is the parent going to do? Okay, so when it returns to the parent, then the context over here, okay, and the other stuff in the process control block, okay, I put a question mark over here because now this parent process is starting to execute. When it executes and it becomes out of sync, the process state information become out of sync from its process control block, right? Because it's running in the processor, right? If it's running in the processor, well, who is updating this data over here? Nobody, right? So therefore, it becomes out of sync. Okay? If you look at the child process is suspended. Okay? So therefore, the child process of the state of the child process is exactly what's stored in the context inside the operating system. All right? So now the parent continues to execute. The parent is going to execute, what is going to execute? It's going to execute the return value for the fork. Okay, it's going to get the PID not equal to 0, so therefore the parent is going to go execute the next statement over here. Okay? All right, and what about the child? If you return to the child, okay, you can do this simultaneously or not, right? Return to the child. In this case, the child will execute. The child will execute again in this exactly the same statement. In this case, the child will reevaluate the return value of the fork equal to 0, so the next thing it will do is try to execute this statement. Okay? But if you're running in the child is going to, so in that case, you will restore the context into the CPU, right? Over here, CPU again. Okay? The child will be running, so therefore the state of the child process will become out of sync with its process control block. All right, and if you return to the child, then the parent process will be in a suspended state, so therefore the state of the parent process will be reflected in the process control block of the parent. And if you have two processes, you have more than two processors, then both of these guys will be out of sync with what's going on. All right. Okay, so if the child continues to execute, what it will do is that it will execute the exec L statement over here, right? The red arrow here says it will execute this. Okay, at this point, the child is still the shell process, the login shell. Okay, as soon as they execute exec L, what happened? Okay, wait a second, it's the same thing. All right. Okay, so exec L is a system call, right? It traps into the operating system. The context of the child process gets saved into the process control block, right? So now, again, this process control block right here will have the current state of the child process, okay? And this process control block of the parent is going to be in sync with the parent process. And now you're running in the operating system, right? What the operating system is supposed to do is supposed to destroy the address space of the child process and then replace the address space with the address space of the primes program. Okay, so the operating system is going to take a while to do that. It needs to go read the disk, take a bunch of data, prepare the address space. So this one can actually take a very long time. Okay, I mean, so is fork, right? Fork, you copy the entire address space, so that might take a while. Okay, eventually the child process will become the primes program. Okay, so now it becomes primes. Okay, the child process will finish executing execl, and it will return, okay, so over here, I get this picture. Here, you will return from, from the parent. But in this case, what happens is that you will prepare the context so that it will return. When it returns, it will be executing the primes program. Okay, so where does it return to? Well, it will return to the main function in the primes program. All right, so during this execl, the operating system is actually going to muck around with the context over here to set it up to pretend as if this child process somehow gets trapped in the operating system to start the primes program. So when this guy returns back into the user space, right, what it will do is that it will prepare these contexts as if it's at the beginning of the main program, okay? And then again, the CPU is over here. When it returns, it will take all the context, write it to the CPU, and now the child process will be running the primes program. All right? So the primes program will run, right? Eventually, the primes program, over here, we're going to switch to the parent. Okay, so again, two things in parallel. The parent will be executing this particular code. Okay, so in this example, what it will do is that it will call wait. Wait is a system call, right? So therefore, it traps into the operating system again. Okay, it's going to go here. The parent process is going to get suspended. And now the parent process is actually going to get stuck in the kernel. All right, so the point of waiting for calling wait is to wait for a dead child. Okay, so in this example, the parent has no dead child, so the parents actually get stuck in the kernel. All right, so it's waiting, for a child to die. So the processor might start running other processes, other threads. Eventually, this child gets to execute again. It will finish running the primes program. Okay, when it finishes running the primes program, sorry, I have a typo over here. It says exit 1 over here. The child process is actually, it's running the primes program. So the primes program, we don't see the exit in the primes program, right? Primes program, it runs. When it finishes computing 300 primes, it calls exit. Okay, so at that point, it calls exit, and it will trap into the system call. So there is an exit call, but it's not this exit. So I should remove the arrow over here. Sorry about the typo. Okay, so the child program is going to call exit. Okay, and the exit trapped into the operating system. Okay, the operating system, what it's going to do is that, again, go back to the last lecture. The child process need to go into the zombie state, where the process control block and the address space that can all be cleaned up. The only thing that need to be kept around are the process ID of the child and the return code of the child. Okay, so therefore, I'm going to draw it like this. Okay, the address space is gone. The process control block is almost gone, right? I used the dash line, so it's not completely gone. Okay, at this point, if it switched to run the parent process, okay, because now the parent process has a dead child, right? So therefore, the parent process can actually finish the wait system call. All right, so at the point when the child called exit, okay, the operating system is going to notice that this guy's parent process is actually doing a wait. So in that case, the operating system will say, oh, the parent process, you're allowed to continue to execute. Okay, and when you execute, you will return from wait because now you have a dead child. And in this case, the return code, well, the parent doesn't really care about the return code, okay, but the process ID is going to get returned to the parent. Okay, so at this point, it can return to the parent with the process ID. Okay, and now what happened is that as this guy returned, can you free up the process control block at this point? Okay, for this particular child, the reason you want to keep the child in the zombie state is because the parent hasn't retrieved its return code yet. Okay, but now the parent has finished executing wait, so the parents get the process ID and get the return code, while the parent doesn't really care about the return code. Okay, so therefore at this point you can completely destroy this child process. Okay, so at the time right before wait return, this is the time where the child process get completely cleaned up, and now the process ID for the child process can be reused. Okay, so now you go back to the parent return from wait with the process ID, they compare with this process ID, they're equal, so therefore the parent process is going to jump out of the while loop and go to the next statement. Okay? All right, so over here, I show that the parent process is right here. Okay, and the child is gone. All right, so the picture is a little bit convoluted. If it's confusing, make sure you look at it again, and feel free to send me an email. Come to the office hour if this is not clear. All right. Okay, so the system call is a sole interface between the user and the kernel. Okay, and the system call is implemented as a library functions, and it's a wrapper around the trap system call. Right, eventually called trap, and we just saw some sort of an animation of what happens in that case. When a system call fails, the Unix convention is that so usually when a system call completed, it will return a value 0 or bigger. Okay, when there's an error, it will return a value that's a negative integer. Okay, so if you look at most of the system call will return an integer. Okay, which is 0 bigger, that means okay. Less than 0, that means an error. Okay, so if you look at the man page of write, okay, write, this particular system call, if it returns something, if you look at the man page, it will say when it returns -1, that means there's an error condition. Okay, but what kind of error condition? Okay, so it turns out that there's a global variable called error number that you can, read that, and then that will tell you what the error is. Okay, but that's just an integer, so it's very confusing. You don't know what it is. One thing that you can do is to call the function p-error. Okay, so you can call p-error, give it a string, some kind of descriptive thing to tell you what your program is doing, and it will tell you, and it will print out. So p-error stands for print error. It will print out why this particular system call failed. Okay, so when you try to perform the write system call, or maybe the file system is full and you can't really write to it anymore, or maybe some other strange stuff happening in the operating system so that you can't write to this file anymore. Okay, so in that case, you do this to find out what the error is. Okay, and every system call, you have to check the return code. Okay, get into a habit of always checking the return code for every system calls. All right, over here, this picture sort of shows you what the address space actually look like in Unix, and also in Windows, sort of looks something like that. Okay, the address space, I used to say that while I sort of start at memory location 0, right? Go all the way to 0xFFFFFFF for a 32-bit machine. Okay, so it turns out that's not really true. The higher address space is actually reserved for the operating system. Okay, so starting from some point, I think on Linux and your kernel assignment, this location is 0xC10000000. Okay, so starting at this particular location, anything above it, is the kernel portion of the address space. Okay, so if this entire thing is 4 gigabyte, okay, then the operating system is 1 gigabyte, and then the user process is 3 gigabyte. All right, so the top of the user address space is actually 0x, right below there is 0xBFFFFFFF. Okay, so the user space is between 0 and BFFFFFF. But then again, location 0 you can't really access. So there's something at the bottom you're not allowed to access anyways. Okay, so we're starting to lose the address space a little bit at a time. Okay, so on top of that, this is the kernel portion of the address space. If your program tries to access anything over here, then that's a access violation. You will trap into the kernel, and the kernel will kill the user process. Okay, because you were really not supposed to peek into the kernel. Okay, so what's in the kernel address space? Well, it's just like the user process, right? Over here, there's the code segment, there's data, there's stack, So the kernel sort of look, like the user space. Okay. when you make a system call, when you trap into the kernel, okay, so what happens is that you were executing user code, right? You make a system call, the system call set things up, eventually invoke the trap instruction. When you invoke the trap machine instruction, then all of a sudden the processor, right? So again, this is one of those, trapdoor. You dropped into it to control access into the operating system kernel. Okay, so what the kernel will do in that case, it will change the processor mode from user to privileged. Okay, and then you're starting to execute code inside the kernel. Okay, all that means is that, if you have a CPU right here, okay, inside the Intel x86 CPU, there's something called the instruction pointer, right, EIP. Okay, when you were executing user code, EIP was pointing somewhere in here, okay? And then ESP, the stack pointer, will point something like over here. EBP will point somewhere in the middle of the stack, okay? And then in the CS, the segment register, it says that you're running in the user mode, okay? When you invoke the trap instruction, you're trapping to the kernel, then the code segment register or the segment descriptor is going to say you're executing in the privilege mode, okay? EIP will point to right here. Okay, you'll be executing kernel code, right? And if this is the kernel stack that you're using, the ESP will point right here. Okay, and then EBP will point somewhere inside this kernel stack. All right, so it's almost like a function call, right? That you are here, you're calling the right system call or fork or whatever it is. All of a sudden, you're executing right here. You're using a different stack, okay? And your code segment, your program is executing different code because right now you're executing kernel code, right? The kernel code is going to perform the service to help you to write to a particular file. Okay, so over here I asked, is this the same thread of execution? Okay, user thread is executing this code, right? It makes a system call, and then a few milliseconds later. Okay, so actually there's some magic happens. It's called the hardware abstraction layer. Okay, and then, a few milliseconds later, you're going to execute code right here. Okay? Is that the same thread of execution? So the answer is both yes and no. It's yes because, you're basically making a function call, right? And then, this thing executing the kernel, well, there's no way for it to execute concurrently with the user, thread. Okay, so therefore, it's kind of like the same thread of execution. Right? You're either executing over here, or when you're done, you're going to return back in over here. So this thing that's running in the kernel, it's like a continuation of the user thread. Okay, so one way to look at it is that when you trap into the kernel, your user thread basically changed mode from the user mode to the privilege mode, and then you jump to a different memory location. Okay, and you use a different stack. Okay, so basically the kernel thread is like an extension of the user thread. All right, it just has more privileges. So it's doing things on behalf of the user. All right, so that view is fine. Another view is that, the kernel thread are so the kernel run a bunch of threads. Each one of them is waiting for somebody to make a request to the kernel. Whenever you go through the trapdoor and you say, I'm making a request, the kernel is like a server. It will allocate a thread to say, I'm going to serve you with this particular thread. Okay, and that server thread running the kernel, so, it's executing kernel text. It's using a kernel stack, and stuff like that. Okay, so that view is also okay. Okay, so the kernel is basically a collection of kernel threads that are trying to serve the user's thread. When the user make a system call, the user thread is suspended. The kernel thread go do stuff for it, and then return and activate the user thread again. All right, so either view is fine. Eventually, when you do the last kernel assignment, you sort of see how this actually works. Okay, in the kernel 1 assignment, you will be implementing only the kernel thread. So kernel 1 assignment, you're going to not do it with the user space at all. You're going to see what kernel thread looks like, and eventually you're going to see what's the difference between kernel thread and user thread. All right? All right, so when the kernel needs to support multiple user processes, okay, so over here, this picture, here's the, process 1, process 2, process 3, process 4, and every one of them, they could all be making system call at the same time, right? Even though if you have a user, one CPU, okay, this guy will make a system call. So, the EIP is going to point right here. The ESP is going to point right here. And then if this guy is waiting for something to happen, and it gets stuck in the kernel. Okay, another process is going to execute. This process make a system call as well. Okay, maybe it makes a different system call. Okay, and now for this process, EIP is going to point right here. They can't use the same stack, right? If you use the same stack, it's going to wipe out, what the kernel is doing for this user process. So therefore, it has to have a different stack. Okay, so in that case, this process, when it goes into the kernel, it's running a different kernel thread that's using a different kernel stack. All right, because at that point, you can't really share the same thread, because then you will share the same stack, and then that's no good. Okay, so therefore, you have to use a different stack. So in the end, you're going to end up with a different thread in the kernel that's handling this user process. Okay, and then it can get stuck in the kernel again. This guy is going to make a system call, so this guy, use another kernel thread, and then this guy do the same thing, right? So in the end, if you look at the kernel is basically just one big giant process, has many, many threads of execution. Every one of these threads is trying to support a user, process. Okay, and the kernel may actually have their own threads. Some of the threads are doing I/O. Some of the threads are, keeping other data structure intact and stuff like that. So there are tons of threads that's running the kernel. Every thread that's running require a stack. Okay, why is that? Right, because when you execute C code, the function argument, and the local variables, they live in a stack. Okay, so therefore, if you have a different thread, you have to have a separate stack. Okay, otherwise the kernel thread is going to run into each other. Okay, so every kernel thread has its own stack. All right, the kernel is like one giant process. Is there any reason to protect one kernel thread from another kernel thread? No, right? Because it's the kernel. The kernel is very powerful. If one thread decides to kill another thread or trash the memory of another thread, it should be allowed to do that. It's the kernel. Okay, it's the most privileged, thing inside this machine, so they should be able to do whatever it wants. Okay, as it turns out, when you're starting to do kernel 1 assignment, you will see that inside the kernel there are actually multiple processes. Okay, so the kernel process and the user process are a little different. In the user process, the process is represented by an address space. Okay, and then one user process cannot write into the address space of another user process. Okay, in the kernel, it's just one giant, kernel process address space. So therefore, any kernel process can actually write into the memory of any other kernel process. Okay, so why do you really need, kernel processes in the kernel? Okay, the reason is that it's sort of a convenience. It's kind of a nice abstraction so that you can actually have one kernel process wait for another kernel process to die. All right, the code that we saw for the user case, you can call wait to wait for another process to die. And turns out that's a very useful concept that can actually be used in the kernel. Okay, so therefore what you can do inside the kernel is that you can group a bunch of threads together. You say these few threads, I'm going to group them into a process in the kernel. Okay, and then I can say I'm going to wait for this process to die, which means I'm going to wait for every thread in that process to die. And then, your code can be much cleaner. Okay, so we end up doing, kernel processes because it's a good programming abstraction. Okay, but in reality, we only need one giant process. Okay, but the problem with having, one giant process is that if you have one thread that's waiting for another thread to die, how do you really say it? Okay, how do you say that this thread wants to wait for another thread to die? So it turns out it's actually, very difficult to say that. So what you do is that you put things in a process that I want to wait for that process to die, and you just call the wait system call, very similar to the user space wait system call, slightly different, but the idea is the same. All right, in the kernel processes, they cannot make system call because the system call by definition is an abstraction that are used by the user processes for trapping into the kernel. Okay, once you are inside the kernel, your program should be perfect. Your kernel is not allowed to have bugs. Okay, so therefore, you don't really need to make system call. You just go ahead and access whatever you want to access. Okay, so hopefully, your kernel won't have any bugs. All right, so that finished the introduction of processes. Later on, we're going to talk about threads in Chapter 2. Okay, so right now we sort of stick to the idea of processes and threads, they are the same thing. When we go into chapter 2, one process can have multiple threads. Okay, we're going to start looking at that abstraction. All right, and then the next thing we're going to do in chapter 1 is to have a brief introduction to files. If you have read my post in the class Google group, I sort of explain a little bit about standard input and standard output. Over here, we're going to see a little more about it. Okay? All right, so what is, why do we need files? And the reason is that, the primes program that we've written, right, compute the first 300 primes, and then the program dies. Okay, it's not very interesting because, what if the code is implemented incorrectly? As a user, how do you know? Okay, if the program doesn't do input and output, okay, so the programmer actually have no idea whether the program is running correctly. Well, they can run debugger to find out, okay, but that's really not a good way, right? Eventually, you want your program to be used by user, so the user, in order for them to find out what the program is doing, it needs input and output. The user cannot just peek into the address space of the, the program to say, oh, you're doing the right thing. I know what the first 300 primes are. Okay, so therefore, you got to have a way to, to have an extension of your address space, right? The user processor, here's the primes program. Okay, it's computing stuff, right? In the end, I guess the last example we saw, there's the heap area over here. Over here, you have an array of 300 primes, right? It finished computing all the primes over here. You need to have them, you need to send them to the user. Okay, if my user process, the only thing that I can access is my address space, then what can you do? Right? You can just put it in a different place in the address space. So it's really not very interesting. Okay, so we got to have an extension to the address space where this program can communicate with the external world. Okay, for Unix, this way to represent the external world is using the file system. All right, so the notion of the file in the Unix system is the sole abstraction of this concept of somewhere else, somewhere outside of the process, right? The process is this address space. If you want to access somewhere else, well, you have to use a file. Okay? Modern Unix systems have additional abstractions. So far, for the 6th edition Unix, the folks of this class, we're going to talk about this files abstraction. And later on, when you do the kernel assignment, you're actually going to implement some of these things to see how you communicate the information over here from here to the external world. Okay? So the file is an abstraction of persistent data storage. When you write to a file, it stays on, on the disk somewhere, and later on, you can read the data back into your program. Okay, so it's a way for your program to store something, outside, and later on, read it back for the next time when you run your program. Okay, it's a means for fetching and storing data outside of the process. Okay, and this thing could be, the place you write could be the disk. Okay, but it also could be you can actually write it into another process. Okay, if you're running inside your process, you want to write something out. Well, maybe there's an abstraction for you to represent, so you can write to another process. Okay, so one of the examples that we already see is in the grading guidelines, right? You run 2 child processes and you pipe data from one place to another. You use the pipe character, which is the vertical bar. And as I mentioned in the class Google group, what you're doing is that you're connecting the standard output of the first program with the standard input of the second program. And now you have data to go from one process to another process. All right, and that's using the file abstraction. Okay. You can also read the keyboard, right? When we're typing on the keyboard, you read from standard in, somehow the keyboard is connected to the standard input of your program. Okay, so again, that's going through some sort of a file abstraction so that when you read from standard input, you're reading what the user is typing. Okay, so again, there's, you go and type into the operating system does some magic, and then whatever that get typed on the keyboard gets sent to your user process. And again, that data that you're reading, it doesn't come from your address space, right? It's come from your standard in, which is, just some sort of a file, handle you read from, and then this external world stuff coming into your user process. All right? When you try to print something, you do a print to standard output. That thing show up in your display. Your display is a device. Okay, so again, you're using the file abstraction to send data to a device. All right, so you don't really talk to the device directly, right? You use the file abstraction in your program to talk to all these external devices. All right, so over here is etc. because there are many, many things that you can communicate to. If you want to communicate to the internet, again, you're going to use some sort of a representation of a file. You can read from this file, and boom, it goes across the internet, fetch some data, and then put it into your program. If you want to write something to the internet, you can also do that. Right? You fill out forms. That's going the other direction. All right, so you need to have a way to name all these different places. Okay, inside the file system, we have a hierarchical naming structure, and that's adopted by almost all the operating systems these days. Okay, unless you have some special purpose operating system that's only supposed to do one thing, then maybe you can name things a little differently. But most of the popular, general purpose operating system, they use a hierarchical naming convention. All right, so the file is also known as part of process's extended address space. Okay, so process can access anything inside the address space. Okay, when it needs to use the extended address space, so where is the extended address space? Okay, so if this is the user process inside the operating system, we saw process control block, right? Process control block, the user process don't have direct access to the process control block, because if it does, well, then you are touching the kernel. You're not supposed to do that, right? So if you want to touch anything inside the extended address space, right? So this is an extension to the user process. You can also have files inside the operating system kernel. Okay, so they're extension to the user address space. In order for you to access them, you have to make system calls. All right, so for example, file cursor position is part of this execution context. Okay, when you try to access the file, you open the file, right? You probably do that already in warm-up number 1, right? You open the file, you start reading it. Okay, when you read one line at a time. So how does the program know that when you do read the second time, you need to go to the second line and not read the first line over and over again? Okay, somebody's memorizing that for you, right? So what happens is that inside the operating system, it actually keeps track of that. When you finish reading the first line for that particular file, there's something called the cursor position, okay, or file position. That remember that if you read the next time on the on this particular file, it will start reading from here. Okay, so is that part of the context of your process? Okay, if your process needs to go to sleep, does it need to remember that? When it comes back, when it try to read again, it will read from the right place. Right, so therefore the answer is yes. Okay, so all these things are considered part of the execution context. Okay, so in this case, this context, the cursor position for a file that your process has opened, it's not in the process control block. Right, the process control block belongs to the the processes subsystem. Okay, and these files belong to the file subsystem. Okay, and again, these context information are spread out all over the place. All right, so we're going to look a little more detail at these things. All right, to name things, we use a directory system. They're shared by all the processes running on the same computer. Okay, and then so this sort of define a namespace. So the namespace is how you name things, right? We use the word namespace. It's outside of the processes, and usually they're represented by strings. You give something a string to say, I want to name some object in the file system. So I give it a string, and the operating system look at the string and say, oh, I know where it is. I'm going to go get it and then return to you. Okay. Similarly, when you want to access something across the internet, right? You use a URL. URL is a way to specify an object in a namespace, and now you give it to the web browser. The web browser says, I know where to get it. Right? It's going to go through multiple protocols across the internet, and eventually you're going to pull down some data and get the data will go into the browser. All right, so it's a similar concept over here that you have a way to name some object, and then you make a request to the operating system, and the operating system is going to know what to do. Okay, so the user process will provide name of a file to the operating system, and the operating system, what it will do is that. So what does it do, right? It returns a handle to be used to access the file. Okay, it's basically going to return to you an identifier so that later on you can say, I want to use the same file. Okay, so for example, if you want to open a file for reading, right, the first time when you open it, it's going to return to you a handle. Okay, if you use fopen, it's going to return to you something of the type, F-I-L-E, capital F-I-L-E star. Okay, if you do open, then it's going to return you to an integer. Okay, whatever it is something that represents that particular file. Okay, later on, you can use this handle to say, I want to read from this file, and I want to read it again, I want to read it again, I want to read it again. Okay, so this handle is sort of a very important abstraction that will use something in the operating system, right? Because the operating system is keeping track of the state of this file for you inside the operating system, and when you want to refer to it, you pass the handle back into the operating system. Okay, using a handle. Okay, so what's a handle? Okay, well, a handle could be something as simple as an index into a kernel array. Okay, so you're going to get integer 0, 1, 2, 3, 4, 5. That's an index into a kernel array. You have no idea what's in the kernel array. All you have is an index. You say, I want to access file number 17. Right, that's fine, right? So over here, it's an index into a kernel array. Okay, also could be a kernel memory address, okay, which you're not supposed to access directly, because if you access directly, you're going to get a segmentation fault. Okay, but if you pass that address into a system call, the kernel will say, oh, I know what to do with it. Okay, so all these things are, generically called a handle. Okay, it's just something that represents an object inside the operating system. Okay, so using a handle to refer to an object managed by the kernel is a very important concept. Okay, so the operating system actually can maintain a lot of context information, and every piece of context, if it wants the user to be able to do something with it, then what it will do is it will return a handle to the user process and say, next time if you want me to do something with it, just give me back the handle, and then I will do it for you. All right, certainly with files, you're going to return a handle for that. So handles are essentially extension to the process's address space. All right, so again, if you look at that user process, if this is the address space, when you get a handle back, where do you store the handle? Okay, if you call open, it's going to return you with the integer. If you call fopen, it's going to return to you with a pointer of some sort. Okay, you store that in the stack, you store that in the heap, you store that in the global variable, right? So you keep track of your handle inside your address space. Okay, but where the handle points to, where the handle refers to, is inside the kernel. All right, that's how you, ask the kernel to do something. Right, so therefore, this is an important concept. Okay, over here, there's a note to say that these things can survive execs. Okay, so what happens when you have an exec, when you call exec? Okay, when you call exec, the address space gets destroyed. You're going to create a new address space with a new program, right? Okay, so the entire address space is gone. Okay, but what about your extended address space? Actually, the extended address space is still maintained exactly the same. Okay, so this is also how the kernel does the magic. Okay, when you're running one, using one address space, running one program, when you say exec, you're running another program. Okay, but now you can actually have a way for your the old program who is dead to communicate with the new program, to pass data from the old program to the new program by passing along this data structure that are inside the kernel. Okay, but is there a way to pass a pointer from the old process to the new process? Right, if you store something inside this memory location over here, you try to pass it to the new process, well, it get wiped out. So there's no way for you to pass it. Okay, but if it's an integer indexed into a kernel data structure, right, the number 3, let's say I have a number 2, I want to pass from this guy to this guy. Okay, 2 refer to some kernel data structure, index number 2 inside this data structure. When you go to this other program, what it will do is that if it just use index number 2 to access this data structure, the data is still there, right? So the old user process can actually write to this memory location 2 by making a system call to do something to location 2, and then when you run this other program, it will say, I'm going to go access that location 2 in the kernel again, so I'm going to pass the number 2 inside the kernel, and now the kernel will be able to use that information. All right, so even though you're doing an exec, there's actually this tricky way to pass from the dead process to the one that's about to become alive. All right, again, we're going to see an example of this pretty soon, okay, in today's lecture. All right, so let's look a little more about the file abstraction, right? A file, so the abstraction of the file, when you try to read and write to the file is an array of, a file is a simple array of bytes. Okay, the file doesn't really contain characters and stuff like that. That's just, that's sort of an illusion. Okay, the file is just a collection of bytes, Okay, it's an array, so you can go read the first byte, the second byte, the third byte. Oh, sorry. Array index go from 0, right? It goes 0, 1, 2, 3. The size of the array, let's say, is n. So then you read the last byte is n minus 1. Okay, then you read in the entire, array. Okay, so you can actually read this the data byte sequentially when you call, read or write, or you can actually have random access to jump to a certain location and say, I want to read byte number 10,000 in that particular file. Right, but a file is just a collection of bytes. Okay, somebody says, oh, file extension. I mean, all those things have no meaning. Okay, the file name is you just name a file inside the namespace. Okay, and once you open the file, it's just an array of bytes. Okay, it depends on how your program interpret it. If it turns out to be Excel spreadsheet, right, then when you open it, then you say, oh, byte number 0 got to have this meaning, byte number 1 has that meaning, etc. Okay, so it depends on how your program interpret it. Okay. The files can be made larger by writing beyond the current n. Okay, so if you have a file that's this big, right, go from 0 to n minus 1. Okay, if somehow you can go, have your cursor position point here, okay, or, file position, okay, if your cursor position pointing over here and you write to it, the file becomes bigger. Okay, so that's a simple way to make the file bigger. It's just somehow you need to go here and then, write beyond that. The files are named by their path in a naming tree, right? So that's the namespace, okay? And then we use the, the slash character to indicate the root of the file system, followed by, for example, slash user bin, ls or something like that, right? This is the root of the file system, hierarchy, okay? Inside that, there's a directory called user. Under the user directory, there's another directory called bin. And under bin, there's a file called ls, and that's how you name it. Okay, and we all, also see the example of how you name the primes program, etc. All right. To interact with the file, you need a bunch of system calls. Okay, the file system related system call are all synchronous. Okay, synchronous in the sense that when you make this function call, the function will not return until the operation is done. Okay, so for example, if you call write system call, when the function write returns, you sort of know that the data has been written to disk. Okay, the data has become permanent. Okay, so the idea over here is this particular abstraction is that function will not return until write is completely done. Okay, when you make a read system call, read only returns when the data are fetched from the disk, get put into the memory buffer that you supply in the read. So as soon as the function returns, you can look at the buffer, and those are the data that you read from the disk. Okay, as opposed to an asynchronous system call, when you call it, the function returns right away, and then you have to keep asking, is the data there, is the data there, is the data there? Okay, that's a different modes of interaction. Okay, so by default, all the file system call are synchronous. If you read the stuff on the internet, it says, oh, maybe sometimes you want to turn these into asynchronous interfaces. In this class, you should try not to do that. Okay, maybe in other classes you can do it, but in this class, you want to keep things, synchronous. Okay, so the syntax of these the way these functions operate will be very, very clear to everyone. All right, so file system API is actually very simple. Okay, the basic, there are only 4. Use open to open a file. Open will return to you a file handle, and use that file handle to call read to read data from the file. You call write to write to that particular file, and then you call close if you're done with that file. Okay, there are also other APIs. So for example, if you open a file, you want to go to the end of the file. Okay, because you want to basically make the file longer, you want to append to the file, right? That's a different API. So we're going to talk about that a little later. Okay, the basic one is very simple, just open, read, and write. Okay, and then close. All right, so here's the example, right? So what the file system call are open, read, and write, and what they return in this case is an integer. Okay, the integer is an index into something called a file descriptor table. Okay, so the idea over here is as follows. You have your user process, okay, and inside the operating system over here, there is a file descriptor table. Okay, file descriptor table points to a bunch of files that are open for your process. Okay, so here's a user process. Here's a file descriptor table for this user process. So these two things are linked. So every user process has its own file descriptor table inside the kernel. Okay, and then what you do is when you open a file, what you return is going to be the index into the file descriptor table. So they only return an integer to you. Okay, so over here, this example, over here you have a place to store the return value of open. Okay, it's an integer. FD stands for file descriptor. Okay, so FD is equal to open. You try to open this file. The next argument tells you how you want to open it. I want to open this file for reading and writing. Okay, so over here it's O_readr, RDWR, reading and writing. Okay, so this is going to be a system call. It goes into the operating system. The operating system is going to use the string to sort of figure out where this particular file is. Surprisingly enough, this one is going to take a while to find it. Okay, because what the operating system needs to do is to sort of, go through different places on the disk in order to find this particular file. Okay, the system call is going to take milliseconds, and also when it's trying to do that, it needs to verify that you have the permission to open all these directories and to open that file. Okay, eventually when the operating system has done all that work and figure out that you have the permission, find the file, what it will do is that it will open the file and keep track of that file in a kernel data structure. Okay, and they're going to allocate a file descriptor entry inside the file descriptor table, and have this guy point to this file that has just opened. Okay, it's going to return the index into this table back to your user process. Okay, so in this case, FD might be equal to 3. This is the first thing that you do when you run your program. Okay, so 012 is reserved, and I mentioned before 012 is standard in, standard out, and all that kind of stuff. I think it's on the next slide. Okay, so over here, once you open it, it's going to return to you a file descriptor, which is just an index into the file descriptor table. So later on, if you want to read something, you pass the handle back into the system call. Okay? So when you say read, you say, well, what file do you want to read? I'm going to read the file that's represented by the file descriptor. I want to read 1024 bytes from this particular file, and this 1024 byte will go into this buffer. Okay? So this buffer better be large enough to hold all the data. Right? So over here, I declare buffer be 1024 bytes long, and I will go to the beginning of the file. I will read 1024 bytes. Okay, if I try to read it again, the next time when I read, inside the kernel over here is going to remember that you have read 1024 bytes already. So next time when you read, it's going to start from location 1024 and continue to read from there. All right, so the cursor is kept track of things inside of the operating system. Okay, and then the file descriptor table is also inside the operating system. All right, so here are the standard, the first 3 entry in the file descriptor table have, special names for it, okay? Entry number 1, right, again, this is, oops. Okay, this is the operating system. Here, the file descriptor table for your user process, 012, location 012. Location 0 is referred to as standard in. Okay, location 1 is referred as standard out. Location 2 is referred as standard error. Okay, so these things actually point to special places. Okay, so if your process gets started by the login shell, and the login shell is reading from the keyboard, okay, and then it forks off a child process, right? So let's say that you start with your login shell. This is the parent process. It forks off the child process, which is going to run your Walmart number 1 program. Okay, when the parent process is going to have a file descriptor table. And, the parent process is the login shell, so it's reading from the keyboard. So therefore, standard in is somehow connected to the keyboard. Okay, and the login shell, when it tries to print something on the screen, well, it shows up on the screen. So therefore, its standard out is connected to the monitor. Okay, and the standard error, if the login shell want to print error messages, they also appear on on the monitor. So therefore, I guess 1 and 2 sort of point to the same thing. Okay, when it forks off a child process, right, here's the child process. Every process has its own file descriptor table, right? So therefore, when you make the fork system call, the operating system will create a file descriptor table for the child process. All right, and then it will copy this entire content into this array. Okay, so therefore, what was 0.2? Well, 0 will point to the keyboard. 1 and 2, they will both point to the same thing. All right, so when you do a fork, the child and the parent, they're actually sharing all the same files. Okay, and then what you do in the child is that you say if fork returns 0, then you call it exec, right? Exec. Let's say you're loading your warm-up 1 into the child process. So now the child process address space will be destroyed, and now it will start running your warm-up 1. Okay, but this part, the extended address space of your child process, did not get touched. Okay, so now if your warm-up number 1, if you try to read from standard in, where will be reading data from? It will read data from the keyboard, right? Because the fork, the parent has set it up so that the child will read from the keyboard. Okay, so therefore, when this thing get replaced by your warm-up number 1, if you call read, you will read from the keyboard. If you write, you will print to the screen. So that's why when you run your program, when you print to the screen, you're sharing the same screen as your login shell, because they all point to the same screen. All right, so your login shell can actually do funny stuff. Have your program output go to a different go to a file instead. Okay, and that's stuff we're going to see. All right, so anyway, so that's sort of a brief description of standard in, standard out, and standard error. And here's an example of how to use them. Okay, so this program, again, start with main. Okay, what it will do is that it will read the first argument is the file descriptor. So it will read from file descriptor 0, which means it will read from standard in, whatever standard in is. Okay, it could be connected to the keyboard or whatever. So it will read from standard in, and then it will put into this buffer, and this will put in this many bytes, right? Size of buffer over here is buff size, whatever you define it to be. Okay, so it will read that many bytes, put it into buffer, and then the return value of read is the number of bytes that have read. Okay, the number of bytes that's read, it's going to be a positive integer. Okay, so if this value is negative, that means that it's an error. Okay, otherwise it's okay. So then what you do is that you will write to standard out, right? The first argument is also the file descriptor. You will write to standard out, buff, and the number of bytes you just read. So however number of bytes you just read, you write to standard out. Okay? So what is this program? This program is CAT, right? C-A-T. If you've been running the grading guideline, you see the program called CAT, right? All CAT does is read from standard in and write to standard out. Okay, and if you give CAT a file name, it will open that file and read from that file and then send all the data to standard out. All right, so this one read, that many bytes at a time, write it to standard out. If for some reason write failed, when you try to write, the output write actually return code is the number of bytes that get written. So if you tell it to write n bytes, and if it couldn't write n bytes, that means something is wrong. So therefore, we're actually going to print out some error message. I'm going to write to file descriptor number 2, which is standard error, and the data I'm going to provide is this note that's right here. So it's a constant, and then I'm going to write out this many bytes. Okay, so what you will do in this case, you will see an error message saying write fail on the screen, and then it will call exit. Okay, otherwise this program just loops around, keep reading data from standard in and send it to standard out. All right? Not a very exciting program, right? All right, so back to primes, right? So we can change our program to do something interesting. We're going to write out the array, okay? So therefore, you can call write, right? After you finish computing all the prime numbers, they are stored in the prime array, right? The size of the array is in argv of 2, right? Okay, in this case, what you can do is that you can write out the entire array. You can say write to the file descriptor 1, which is standard output. The starting address is going to be the prime array over here, and this one is pointing to the heap somewhere. Okay, and the number of bytes is going to be 300 integers, and every integer is 4 bytes long, so it's going to be 1,200 bytes. So therefore, you start with that memory location. You write out the number of primes times the size of int. In this case, it will be equal to 1,200. Okay, so when you write, if you get a -1, then write fails. Right? Otherwise, this data will appear on the terminal. Okay, but unfortunately, the data is going to be in binary form, so therefore it's not readable by human. Okay, so you're going to get all kinds of garbage on the screen, right? To make things readable by human, you use the printf. Printf is a formatted print. So if you read the man page of printf, it says format, the output. So what does formatting mean? Well, you format it for human reading. Okay, the previous case, machine can read it, but human can't read it. So now you format it for human reading. You can print out a bunch of all the primes, followed by carriage return. So you're going to see 300 primes get printed on the screen. Okay, so now this program is a little more interesting because you know what the result of the computation of these primes. All right, so when you call open, there's actually a rule of how to allocate file descriptors. Okay, so if this is the file descriptor table inside the kernel, file descriptor table, okay, when you try to allocate a file descriptor entry, what it will do is that it will actually scan the table to find the first available entry. Okay, so by default, 0, 1, 2, they're all taken, right? 0 standard in, standard out, standard error, they're all taken. So in that case, in our example, that's why I said that, the file descriptor is going to be equal to 3, because 0, 1, 2, they're actually pointing to something. Okay, so you will go down this list, find the first available entry, and that's the one that you're going to allocate, point to the file, and return this file descriptor entry. Okay, so if you know that this is the rule, you can actually do something funny over here. Okay, so in this code, what I will do is that I will actually, before I open something, I will close file descriptor 0. Okay, close file descriptor 0, right? So this file descriptor 0 was pointing to the keyboard before. Once I close it, this thing become available, right? Become a big 0 over here. This entry now doesn't point to anything, it becomes available. So next time when I call open, I say open file for read only. Okay, what file descriptor is going to get returned over here? It's going to return to be 0, right? Because I'm going to follow this rule, scan from over here, find the first available entry, and that's going to be, be returned. Okay, so in that case, the first available entry is going to be location 0. And again, when you call open, right, it's going to go to this file, find this file, take milliseconds. Eventually, when it finds this file, it's going to allocate something in the kernel, and find location 0, have this guy point to this file, set up the cursor position, all that kind of stuff over here, and then it will return 0 into the user program. So why do you want to do this? Okay, because once you do this, if the user program calls write to standard out, if the user program read from standard in, what's going to happen? If the user program says, I want to read from standard in, what it will do is that it will go to location 0, and then it will read from this file. Okay, so the previous code over here, where's the previous code? Okay, so this code over here that's reading from standard in, now it's going to, instead of reading from the keyboard, it will read from a file. Okay, all you have to do is make sure that you call that, you do the close and do the open before you do any of these things. Okay, and then you can actually have these strange behavior. All right, so now we're going to see how that actually works. Okay, so in this case, what we'll do is that we'll go back to the parent-child process again. The parent process is going to call fork, right? And now the parent and child is going to run in parallel. The child is going to come over here. The parent is going to go over here and wait for the child to die. Okay, so now we ignore the parent because the parent is just got stuck in the operating system waiting for the child to die. The child process will call close number 1. Okay, so it will close the standard output. Right, so over here, 1 used to point to the terminal. Okay, so now it points to nothing. It becomes a null pointer. All right, and then it will open this file for write only. Okay, so what happens is that you go to home BC output. That's a file. You're going to open that file for writing. In the operating system, you're going to allocate this entry that corresponds to this particular file. Set up the cursor position to location 0. Okay, and then you're going to find a file descriptor, the lowest available file descriptor. You're going to allocate that file descriptor to point to this file. All right, so now this guy again is going to become a pointer. Point to this entry. Okay, and only at this point, then I will call execl. All right, so in the parent process, I actually set all these extended address space stuff up right before I call execl. Okay, so in this case, when the execl is called, I'm going to run this program. The primes program, what does it do? It computes 300 primes, right? Over here, 300 primes, and it will print the output to standard out. Okay, so when the child process starting to print to standard out, where would it go to? Right? You will use file descriptor 1 to say, hey, operating system, write this data out to file descriptor number 1. Okay, so it turns out operating system follow this pointer, it will go into the file and not go into the display. All right, so this is basically what your login shell is doing. Okay, your login shell, what it will do is that, when it notices that the user types something like this, primes 300, right arrow, so this is called IO redirection, it will say that the output of this file, the standard out, instead of going to the display, okay, instead of going to the standard place, what it would need to go to is they need to go to this file. Okay, so this program is actually your login shell, which is, C shell or TC shell. Okay, inside that program, you're going to see code like this. It will fork, so what it will do is that it will execute this code if it sees a greater than sign in the command line. Right, so then what it will do is it will pass this thing to the first argument of open. It will, before that, it will close the standard output. Okay, and then eventually it will execute this particular program. Okay, it will pass these strings into the arguments of execl. And now when your program is running, your output actually goes to this particular file. Okay, so your login shell is actually doing all these tricks. Okay, the login shell, take a user command. Most of the time, your login shell just sit there waiting for you to type something, right? As soon as you type something, it will parse whatever you just typed, try to make sense of it, and decide whether you have done some things like this or not. If you have done things like this, then it might have to close some file descriptor, open something up, and do all kinds of other things. Okay, so you can do the things with standard output. You can also do the thing with standard input. So for example, if you run your program like this, cat less than /home/bc/output, okay, it sees the less than character, then what it will do is it will close the standard input, okay, open up this file as the standard input, and then it will call exec. So now, in the exec, it will run the cat program, and the cat, in this case, when it try to read from standard in, it will read the content of this file. Okay? And then there are other syntax, right? You can write one program and pipe it with the other one, and now, again, the login shell will need to create 2 child processes, connect the standard out of the first program with the standard in of the second program. So the first program, when it tries to print the standard out, it doesn't show up on the screen. It will go into the standard in of the second program. So when the second program tries to read from standard in, it's going to read from the keyboard. It's going to read from the output of the first program. Okay? In the grading guideline, right, we see this is cat, this is warm up 1, etc. All right? Okay, and this is called IO redirection. Okay, so the file descriptor, referred not just to a file, right, just an index into, it refers to all the stuff that's happening in the kernel, right, the extended address space of your user process. Okay, it refers to the process's current context of that file, including, cursor and stuff like that. Okay, so the question is that what should be in the context? Okay, the context the operating system is keeping for your file. Okay, so the context, one of the things that the context has to remember. Okay, so remember that the way that you use these APIs to talk to the files, that you're gonna call open. Okay, and then you're gonna say read. Eventually you're gonna call close. Right, you're gonna read multiple times. Okay, the reason this is done is that when you open the file, you're going to check whether whether your user process is allowed to open this file or not. Okay, so you only have to do that once. Okay, because after that point on, every time you call read, you bypass all the access rights check. All right, so therefore all these things are fast. Open is actually very, very slow because you need to verify a bunch of stuff. Okay, and then when they call read, it doesn't have to check it anymore. Okay, so therefore, when you call read, well, you still have to make sure that the user is not doing something funny. Okay, over here, here's an example. The user can actually doing something funny. What it will do is that when it opens the file, it says, I want to open it for read only. Right, here's the file name followed by read only. Okay, and then what if it, instead of calling read, it called write. Okay, so when you open the file, let's say you open a system file, in the root directory, you open some file. Okay, and the operating system says, oh yeah, you're allowed to read it. Give you a, give you a file handle. Okay, give you a, allocate an entry inside your file descriptor table, and then instead of doing read, you actually call write to it. Okay, so how does the operating system know that you're not supposed to write to it? All right, so what happens is that inside of this context that the operating system keep for your process, it needs to remember how you open this file. Okay, because what it needs to do is that it knows that when it opened the file, it performed all these checks. Okay, so you need to memorize what kind of checks did it perform. Okay, otherwise what you will do is you will open a file for reading, and you start writing to it, and you end up accessing files that you don't have any rights to. Okay, so this leads to the next picture. Okay, so the operating system actually looked like that. Inside the operating system kernel. So this picture is a little different. The user space on the left-hand side, okay, and the kernel space on the right-hand side. I can't really draw it top-down anymore. So in this case, what happened is that there is something called the system file table. Okay, the system file table keeps track of all the open files. Okay, so every time what you do is when you call an open, another entry in the system file table is going to get added to it. And inside the system file table, it will keep track of the information for this file. Okay, so what kind of stuff it needs to keep track of? There are 4 things that it needs to keep track of. Number 1 is called the reference count. Okay, so a file actually can be shared by multiple processes. Okay, so therefore it needs to keep track of a reference count. If the reference count is positive, that means that somebody is using this file. If the reference count goes to 0, that means nobody's using this file anymore, so therefore the operating system is free to delete this particular file. Okay, sorry, the operating system is free to delete this file table entry inside the system file table.
The time is 12 o'clock.
But now it's just the operating system information, nobody uses it anymore, it can be freed up. Okay, so inside the operating system, we use this reference counting mechanism to determine whether something can be freed or not. Okay, and we use the reference counting mechanism all over the place inside the operating system. All right, so here's one example. Whenever you see ref count, then you know that it's doing some kind of a reference counting. The second field is called access mode. So when you open the file, when you finish opening the file, it's going to be written into this field. How did you open this file? Did you open this for reading? Did you open this for writing? Did you open this for reading and writing? Okay, so this way, next time when you call write, the first thing that the operating system will check, let's say you want to write to one of these file descriptor entry, okay, it's going to follow, the operating system is going to follow the pointer, look at the access mode, say, did you open this one for write? If you didn't open this one for write, and now you're trying to write to it, then the system call is going to fail. Okay, so again, write can fail also for that reason, say, hey, you didn't open this for write access, so you're not supposed to write to that file. All right? The third field is the cursor position. It's also known as file location or file position or cursor position. So this one is actually going to be integer. When you finish reading 1024 bytes, okay, this one is going to say 1024. Next time you read another 1024 bytes, this is going to be incremented to 2048. Okay, so this way, when you continually call read, or write, you don't have to say where do you want to read and where do you want to write, right? You already specified a file. All you have to do is that you can use the file location to determine in what offset do you want to read or write to that particular file. Okay, the last one, this one is a funny thing. It's a pointer inside the operating system. Over here, it's another pointer. It's called an inode pointer. The inode pointer is kind of vague. It's kind of an indirection that we use, okay, to point to something deep inside the kernel. So if this is the actual file, it might point to something that represents the actual file. Okay, but this could also be a terminal device. Okay, in that case, this one doesn't really point to a file. It points to something that represents a terminal. If this one is the keyboard, it will point to something that represents the keyboard. Okay, so this is kind of a funny pointer. Over here, we're going to just call it an inode pointer. But you should remember that the inode pointer doesn't really have to point to an inode. It might point to some funny stuff. All right? All right, so the file descriptor table is per process. For this user process, the file descriptor is over here. Okay, when you call open, you're going to allocate an entry inside the system file table over here. And then you're going to allocate an entry inside the file descriptor table, have this guy point to the new one, and then return the integer value back into the user process. Okay? And next time when the user call read or write, and you will follow this path, check the access mode to see if it's doing the right thing, and then read or write using the cursor position. Okay? Eventually, when the user process call close, you will decrement the reference count. If the reference count is equal to 0, that means that this entry can be freed up. If the reference count is not equal to 0, that means that some other process is still using this file. All right? Then you keep it around. All right, so so this finishes chapter 1, okay? And so chapter 1, if you look at the book, there's some more stuff. So the rest of the stuff, we're going to do it after we finish chapter 5, okay? Because we don't really need it for the kernel assignment, so we're going to sort of skip ahead and go to chapter 2, and chapter 2 is going to get you ready for the warm-up programming assignment number 2. All right, so chapter 2 is about multi-threaded programming. Okay, so now, so before we talk about processes and threads are kind of like the same thing. Okay, so now inside of a user process, we're going to create multiple threads, and then we're going to sort of pretend that all these threads are running in parallel. Okay, you have no control of who is going to run first and who's going to run next. But if you go to the internet, you're going to see, say, hey, I can teach you how to run something first and run something next. If you see those kind of stuff on the internet, okay, please don't do it in the warm-up number 2 assignment, because you will find out that if you actually do that, your program will be much harder to control. Okay, you say, well, why is that, right? If I want to control who runs next, does not give me more control. Okay, so once you have a way to control who runs first and who runs next, then you're going to make sure that who runs next will actually get a chance to execute. Okay, because it is possible that once you determine that this guy has higher priority over the other guy never gets to run. Okay, so one thing that we're going to learn in this the next few days is how to make sure that all the user threads, they all get an equal chance to run. Okay, and you need to do that by not setting user thread priorities. Okay, ignore the stuff you're going to read on the internet, and follow the stuff that we're going to talk about in this class. All right. Okay. I'm going to skip some of the introductory stuff of multiple, for multi-thread programming. It tries to sort of tells you that, what are the advantages of multi-thread programming. And it's a really sort of important concept. And these days, when you go interview, lots of the major company, they want to make sure that you know how to program using multi-threaded code. Okay, so this is a must. So what you really need to do is you need to, I guess when you do warm-up number 2, you got to do things the right way. Okay, once you learn the right way, then you can write fairly complicated program using multi-threaded program. Okay, and one of the major advantage of multi-threaded program is concurrency. You will have the illusion of you're running multiple things in parallel. Okay, certainly if you only have a single processor, that's not very useful. Okay, but when you have multiple processor, then you actually, your program will run faster. Okay, but if you know that you only have a single processor, do you want to write multi-threaded program? Okay, it turns out the answer is yes. Okay, so here's an example. When you run multi-threaded program, okay, I'm going to sort of skip the detail over here. So there's something called the remote login daemon. Okay, so for example, when you secure shell to Nunkey, okay, you're going to get a greeting from Nunkey to say, login ID and then password. Okay, so that particular process is called the remote login process. Okay, so you're going to be greeted by the remote login process. If you type in your user ID and the correct password, what it will do, it will fork off a user shell on your behalf. All right, so once you type in the user ID and log in, then you will run C shell and TC shell, and then your credential will be presented to the operating system, and then the operating system will create your login shell on your behalf. Okay, so at that point, it's like you are on that machine. Whatever the command that you use, you're running, as your user ID. Okay, so there's this thing before that is called a login shell, and the login shell is the one that can fork off your, the R login D is the one that can fork off your login shell. All right, so the R login D basically is sitting there just passing information, from the internet to that machine that you're connecting to. Okay, if you look at the code, the traditional code of R login D is actually very ugly. Okay, so this code, I'm not going to explain what this thing is doing. Okay, but this thing just passed data along from one side of the internet to the machine. Okay, this code is very ugly. But if you write multi-threaded code, this is all you have to do. Okay, you write 2 threads. One is called the incoming thread. The other one is called the outgoing thread. And all these threads are doing the incoming thread. What we'll do is that it will do a read. Okay, it does a read and does a write. It basically looked like the cat program. Okay, the outgoing thread is doing read and write, actually these two thread code look exactly the same. Okay, if you write a multi-threaded program, the reason, even if you have a single processor, you want to write multi-threaded program, is that your program might be nice and elegant. Okay, so that's one of the reasons that everybody sort of need to learn how to write multi-threaded program. Okay, when you have program this small, okay, so let's say if we go back to the previous page, okay, if I tell you there's a bug in this code, how are you going to debug? Okay, you're going to have a very rough time debugging this code. Okay, if you have a code like this, can you debug this code? Well, it's very simple. You read and write. I mean, how can you go? What can go wrong? Okay, so this program is much easier to write and much easier to maintain, and that's another reason we need to write, multi-threaded code, because now you have very simple program, right? This program, the incoming thing, you stay in an infinite loop and you just do a read and write. Okay, you can actually go to the statement one statement at a time and make sure that this code actually works. Okay, in the previous example, it's like good luck. How do you figure out whether this program works or not? Okay, so hopefully in your warm-up number 2, your program will look like this. All right, you need to, you need to be able to write programs that are very simple. Just look at it and say, oh yeah, it's doing the right thing. Okay, and what you can do is that you can make sure that over here you make function calls. You write all those functions. It's going to provide services for your application. So at the top level, you can actually look at the code and say it's doing the right thing. Right? Then you have to make sure that every little function is doing what they're supposed to do, and then in that case, your thread will be actually doing everything correctly. All right, so learn to write, small threads, nice and clear. All right, and when you write an internet server, over here, example of a database server, okay, you're going to get a lot of connection from the internet. Right? What you can do is that for every connection, you can write a separate user thread, okay, so you can have these things all doing in parallel. Okay, otherwise, it's going to be very, very difficult. If you don't do multi-threaded code, your database server needs to look at 1,000 connections into the database and then try to multiplex the heck out of this thing. Okay, so your application programmer will have to write very difficult code, very similar to the original rlognd. Okay, but now if you write things using multi-threaded program, then every thread will be dealing with one connection, and your code will be nice and simple, right? You read the request from the internet, you make a request to the database, okay, and then you wait for the database to return the result. At that time, your thread will get suspended. You'll run some other thread, make them connect to to other connection, and then eventually, when your data is ready, you just write it out. Okay, so again, your code will be very simple, looking like this. All right, so that's why we sort of use multi-threaded code all the time. Okay, so we're going to jump into section 2.2. How do you create threads, and how do you how does thread terminate? If you do man pthread create, so we're going to talk about something called the POSIX thread. Okay, the POSIX thread is a standard that pretty much all the modern operating system uses this standard. Okay, Windows has their own version. They call it WinSock or something like that. Very similar. Sorry, not WinSock. They have only the Windows thread. The idea is very, very similar. Okay, so POSIX thread, I guess the Mac implementing Unix, so they support POSIX thread. Linux, Unix, they all support POSIX threads. Okay, so we're going to learn the POSIX thread APIs, and you're going to use the POSIX thread API in your warm-up number 2. Okay, so the POSIX thread API again is just an abstraction. Okay, it lets you to to have an abstraction of the threads are abstraction of the processor. Okay, so every thread you can imagine that they're running on a separate processor. Okay, and you can call these things the virtual processor or call these threads. Doesn't really matter. But the abstraction is that every thread is a separate thread of control. Okay, you can run multiple of these things in parallel. All right, the actual implementation actually depends on a lot of stuff. Okay, there's even a question of where do you implement the thread? Do you implement the thread in user space, or do you implement the thread in kernel space? It's like, what does that mean? Okay, but that's chapter 5. So in chapter 5, we're actually going to tell you how do you implement stuff, how do you implement threads in user space, and how do you implement in kernel thread, or even what does that mean? Okay, but at this point, the thread is just an abstraction of the processor. Okay, and we're going to use them to write user space programs. All right, so this is mainly about user thread. Right? So and when you go into the kernel, there's no POSIX thread in the kernel. Okay, so when people talk about POSIX thread, they're talking about the abstraction at the user level. All right, so the user, when you want to create a thread, you're going to call a function called pthread_create. Okay, so this one created another thread. Okay, so it's kind of like fork. Okay, but fork, create a, copy of the address space. So in this case, you're going to have multiple threads running in the same process. Okay, so therefore, if you look at the address space of the process, right, there's only a single process. Okay, have the code segment right here, have a data segment right here, BSS, heap, and the stack. Okay, when you have the second thread also running over here, what happens? Okay, your second thread, right, it's a different thread of control. Okay, so that means that it's still sharing everything as the original program. Okay, so therefore the other thread will have the same code segment, have the same data segment, sharing the same global variable, has the same BSS, uninitialized global variable, has the same heap. The only difference is that the second thread will have a separate stack. Okay, so you're going to actually have another stack for the second thread. Okay, you're going to make sure that they don't overlap the first, the first thread and the second thread. Okay, so every thread actually have a separate stack. Okay, and these stacks are shared inside the same address space of the process. All right, so the address space now become a little more complicated. The bottom part still look the same. Now the top part is going to have multiple stacks inside the top part. All right, so when your program starts to run, you're running the main thread. Okay, so your program has a main entry point, right? The main code, that's where your main thread starts. So every time you start a process, you start with one thread, and that thread is using the stack at the top of the stack. Okay, when you try to create another thread, that's when you actually introduce a new space inside of the address space for the stack of the second thread. All right, so the main thread can call pthread_create to create the second thread. Okay, the second thread, the argument is as follows. The first argument is actually a return thread ID. Not the thread ID, the thread control block. Okay, so over here, you can call this guy the thread control block, right? The process has process control block, PCB. The thread has thread control block called TCB. Okay, over here in pthread, the thread control block is of the data type pthread_t, and that's the data type. Okay, if you provide the address of that data structure, it will return to you something that identifies that particular thread. Okay, so this is the return value. The attribute, usually they're not being used. The third argument is a start routine. Okay, so this one is actually a function pointer. It points to the beginning function of this particular code. So what is that beginning function? Well, it's like, your main thread starts in the function main. Okay, these other threads, they will start at a different function. Okay, so over here you can actually specify the name of the function over here, and that function will get called as the beginning function for that thread. Okay, so over here, I guess we see an example of threads, right? Like incoming and outgoing. Okay, so you can actually just put incoming right here. And incoming, okay, in this case, it's going to take one argument, and this argument is of type void star. Okay, and this function is going to return void star. Okay, and here's the code for the thread. All right, so this is the incoming is going to be the startup function of a thread. Okay, so when you create this particular thread, it's going to start running over here, and this particular code, where is this code? Okay, so this code is part of the same user process, so incoming is going to be somewhere inside the code segment over here. All right, so when this thread starts to execute, the instruction pointer, right, inside the CPU, okay, you're going to have EIP over here. Okay, if the incoming thread is executing, the EIP over here is going to point to the incoming code. All right, and the ESP is going to point to the newly allocated stack right here, and EBP will point to somewhere inside that stack frame. Okay, if you're running still the main thread, so the main thread, when you're running the main thread, then EIP will point to somewhere else in the code segment, and the ESP will point to the the first stack frame. All right, so even if you have a single processor, you can run one thread at some time and switch to another thread and switch to another thread like that. All right, you just have to make sure that the registers sort of point to the right places. Okay, let me come back to this again. Okay, finally, the last argument over here, the fourth argument is the one that you need to pass to the start function. Okay, so again, the start function, right? The example we saw, incoming. Okay, void start. Okay, and this one is the argument. Okay, so what happens is that when this thread gets started, this thing, when you call pthread create, okay, so let's say that the thread that calls pthread create is the parent thread. Okay, so the parent thread is going to create the child thread. The child thread have a start routine called incoming. Okay, so the parent thread will pass argument into the child thread. When they call pthread create, they say, well, take this argument. When you start the child thread, use this argument as the function argument. Okay, this is very similar, right? We have main, which is int main. Okay, and we have int argc, and then char star argv, array or something like that, right? Okay, so when you start the main program, the argument for the main program or for the main thread is actually argv and argc. When you start a child thread, there's only a single argument. All right, and the single argument is going to get passed right here. Okay, so if you read the man page, it's going to show you in the synopsis section that in order for you to call this function, your program must say pound include pthread.h. You got to include the right header, otherwise the compiler is going to complain. And when you try to create your executable, you got to use minus pthreads to link to the pthread library. The pthread library is going to have code for pthread create. If you don't do the last step, then it doesn't know where pthread create is. So therefore, you're going to get an error message saying that function cannot be function reference cannot be resolved. All right, so you use this to create threads. Right. So here's an example called start server. Okay. Over here, the number of server thread. Let's say this is 100. Okay. This function says for I equal to 0, I less than 100, I plus plus. You're going to do the following 100 times. I'm going to call pthread create 100 times. Okay, I'm going to create 100 thread. So when this guy returns, I'm going to have 101 threads running, right? The main threads plus the other 100 thread. Okay, every one of these 100 child threads, their starting location is going to be server, and server is this function over here. Okay, I'm going to take the argument, I'm going to pass it into the arg right here. All right, so this is how you create 100 threads. Okay, so over here, the first one is the return thread identifier or the thread control block. In this case, I'm going to use a variable right here to hold the return value for that particular thread. Okay. Okay. Now I think I'm going to take it back. I don't know if this is actually the thread control block or maybe just an identifier. Okay. But in either case, you can treat them as a handle that actually tell you which thread it is. Okay. So in this case, so over here it says thread identifier. So when you call pthread create, it's going to return to your identifiers. It's going to get into this variable, right? I pass the address of this thread. So when this function finishes creating a child thread, the child thread is going to run in, using this function, okay? And then the thread identifier is going to be written into this variable right here, okay? And now what does the main thread do? The main thread is going to come back over here. I is going to be equal to 1. It calls this function again. And this time it's going to create the second child thread. The child threads, the thread ID, again, is going to be stored right here. So what happened right here? It wiped out the thread ID of the first, thread. Is that okay? Well, your code, right? If you don't care about the thread ID, then it's okay to do that, right? So in this case, actually, when you're completely done, when start server return, this guy, or right before return, this guy will have the thread ID of the last thread. All right, in this case, you don't really care about what the thread ID is, so it's okay. You can actually also provide null as the first argument to say that I'm not interested in the thread ID. So in this case, when pthread create successfully completed, it doesn't return the thread ID anywhere. Okay, but still, inside pthreads or inside the operating system, it knows what the thread IDs are. All right, pthread create should also check the return code. If it returns 0, that means successful. If it returns a negative value, that means that it actually failed. All right? Okay, so this one will show you the address space, right? It's the same size as the previous one, but I'm overlaying the stack on top of it. So now you have 101 threads that are running inside the same address space, right? This is the same user process. Okay, and if you have created 100, threads over here, then you're going to have 100, stacks, every stack actually has a limitation of where the stack begins and where the stack ends. Okay, so the stack of the size of the stack you can actually specify when you create a child thread. Okay, so this way, inside your main program starts in main, right? So you're going to have a stack frame called main over here, and then it's going to call start server, right? So over here is going to be a stack frame for start server. You can actually keep calling function, but eventually, if you go beyond the limit of that stack, then you're going to get a stack overflow, okay? Because then you're going to start writing into the stack space of another thread. All right, so therefore, it is possible that you will run out of stack space. Okay, so now you can have multiple stacks. You have 100 of them. I mean, the address space is pretty large, right? I mean, it's 4 gigabytes of address space, or 3 gigabytes, and now we know. But still, you can create many, many threads over here. Okay, every thread will use its own stack, right? So when you create this guy, okay, what is the top stack frame? Right, the top stack frame is going to be server right here, and this guy is also the top stack frame to the server. They're all going to be server. So you have multiple threads running in parallel. They all start as server, and our server is not very interesting. It just returns 0, right? Maybe it will perform some services, but eventually when the thread terminates, it will call return, and return will terminate the thread. Okay, so the way POSIX thread works is that when you call pthread create, this thread is going to execute in this particular function. When that function returns, that thread is terminated. Okay, when that thread is terminated, then basically that thread, we need to do the same thing because, we have this thread ID we don't want to reuse. And also, what if the parent thread wants a return code of this particular thread? Okay, so the thread needs to go into a zombie state. So again, very, very similar to a process. Okay, when this thread finishes, okay, the thread control block is still lying around somewhere. Okay, we don't want to reuse the thread ID, and we want to keep the return code around for the parent. So eventually, when the parent calls something that is similar to wait, that's when we can free up the thread control block. All right, so make a parallel of that between that and the process. All right, so this particular thread, right, you can actually, we use a stack variable over here, right? We declare pthread, and then we declare the thread ID this way. So this way, when you call pthread create, you can pass the address of the thread ID over here to store the return value. Okay, similarly, you can actually also use the heap. You create a thread pointer, right? Declare a pointer type. You allocate memory for it by calling malloc. Okay, some people forget to do the malloc and go all kinds of crazy bugs. Okay, so make sure you call malloc. You want to malloc the size of the thread ID. Okay, and then when you call pthread create, you can pass this pointer, and then this pointer will contain the the value of the thread ID. Okay, these two ways of doing things are equivalent. The main difference is that in the previous case, if you store things in a local variable over here, right? This guy is a local variable for start server. Okay, local variable live in the stack. Okay, so therefore, when you finish creating all your thread, if you return from start server, okay, then this particular thread ID becomes invalid. Okay, so if you want to use that, you're going to be in trouble. Okay, but if I allocate a thread ID inside the heap, in this case, I might allocate an array of 100 thread IDs. Okay, in that case, I will have them remember. So even when you return from start server, those things will be sitting inside the heap, so you can continue to use them. Okay, make sure you understand. 1 minute left. Okay, make sure you understand how you're going to use the thread IDs. If you need to keep them around, you got to make sure that the memory location where you need later on you need to reference, those are still good memory locations. Okay, and I just want to show you a quick example of, this is the Win32, this is the Microsoft Windows thread. Okay, there's a little gray X over here. That means that you are not responsible for exams, for these things. Okay, so Windows, create thread takes a lot of arguments. All right, so I'm going to stop right here. And on Wednesday, I'm going to continue from here. And on Thursday, I will record an extra session to finish all the thread stuff.
This has been CS402 on Monday, June 2nd, 2014.